There we go.
Yeah. I like this.
I got it. Okay, it's good.
Here we go. Let's see how you did. So let's take a look at chlorine here. How many energy levels does chlorine need to have since it has so many electrons? Okay? Three energy levels. So on the first energy level, 2 electrons. On the second energy level, we're going to put 8. And what do we have left for our outer one? How many? 7. Okay, so we're going to transfer that to our Lewis structure. Remember, we don't take all the electrons with us. We only take the ones that are on the outer shell, the valence electrons. And so for that, we're going to have Cl, our element symbol, and then we're going to 1, 2, 3, 4, 5, 6, 7. So chlorine, we know, has 7 valence electrons. Is chlorine happy? Micah?
No, it is not.
No, it is not. So frowny face, let's make a happy box. What would make chlorine happy?
It's his wish list.
Alex? Yes, to add 1 electron. It is so close to having its perfect octet, to having those 8 electrons. It just needs 1. Chlorine, excuse me, is known as an electron acceptor. Chlorine can be pretty nasty. That's why chlorine in the gas form can actually kill you. It's poisonous. It's because it wants to try and rob electrons off the atoms that you have. So it's an electron getter. Here we go. Sodium. Oh, sorry, Mike, go.
Okay, so I thought on the 3rd layer it was supposed to have 18, not 8.
It's either the shell is full or it met the octet rule.
No, but like for like the 4th one, it's all like its 3rd shell, and I thought that on the 3rd shell it's supposed to have 18.
But it can't. It fits 18.
Oh, the whole thing fits 18?
Yeah.
Oh, okay.
But it doesn't necessarily mean it's going to be full.
Okay.
Alex.
What if, wait, if the element has more, like, the atomic number is bigger, then would there be more, like, energy levels?
Correct. Yeah. There's actually 9 different energy levels, and then there's like suborbitals within them too. Okay. All right. So Bohr diagram for sodium. Once again, I'm going to go a little faster here, guys, just for sake of time. So we got our inner shell. Our our second shell, sorry, has, now I lost count, has 8. And you should have had 1 poor lonely electron for that 3rd shell.
Oh, so that's why,
So our Lewis structure here, we have Na, and we're not transferring all 11 electrons. We're only transferring the valence electron, so just 1. Sodium has 1 valence electron. Is it happy?
No.
No. Sad sodium. What would sodium like to do? Jasmine?
Get rid of 1?
Get rid of 1. It wants to get rid of 1 electron. Okay. Now, in sodium's case, I mean, once you've got 11 kids, what's 1 less, right? Okay, so, I mean, just joking. But it's not the same case as with hydrogen. Remember, hydrogen and helium are kind of our exceptions to the rule. Yeah, Lily.
So that's why salt is so common, because sodium and chlorine, they're just perfect for each other.
They are perfect for each other.
Yep, that's like being good.
Okay, they're made for each other. All right, no, we're joking. Okay, so magnesium here, going to be very similar to sodium. You're going to have your 3 shells, 2 electrons on the first one. We know the drill now, right? 8 on the next one. And then for the outer shell, we've just got 2 electrons left over. So when we put that into our Lewis structure, 1, 2, 2 valence electrons. What does magnesium need to be? Oh, sorry. Is magnesium happy?
No.
No. Okay. Not happy. What does it need to be happy? Elise? Get rid of 2. Yep. Magnesium wants to get rid of 2 electrons. Now, what is something you notice about our 6 atoms that we did here? Micah?
That except for hydrogen and oxygen, if it has like more than half of what it's supposed to have, like valence electron-wise, electrons, like for sodium and magnesium?
Okay, so for these down here, since they have only one or two, hydrogen being the exception, it would rather lose those electrons instead of gaining. Yeah. But the other ones want to gain electrons. Notice that none of our atoms are happy, right? None of them are meeting that octet rule or having their outer shells full. And because of that, this is why atoms bond. It's not because, oh, they just randomly want to like bump into each other and then voila, a new compound is formed. It's because they actually need to get what is in their happy boxes here. Okay, they need to get those things. So in order to do that, there's two different ways. It's either by covalently bonding or ionically bonding. And we're going to start talking about covalently bonding first because C becomes before I in the alphabet, and also because covalent bonds are just nicer and I like them better. Covalent bonds, I want you to kind of associate it with this, unless you don't have this word association, and then that's okay. Just whatever way you want to remember it. Covalent sounds a lot like the word covenant. You guys ever heard of the word covenant? It's sort of a biblical term. But a covenant is basically a promise or an agreement between people, two people or more people, that says you're going to do something. Basically, you're going to hold up your end of the deal. Okay, middle school version, I pinky promise swear you or whatever, okay? So a covenant or a covalent bond is when atoms are actually forming, we're going to call them packs, between each other using their electrons. So our definition here, what we want to fill in, is covalent bonds are formed when atoms share pairs of electrons. Zoe.
So salt wouldn't be a covalent bond because they just share one?
We're going to look at that. Yeah.
Okay.
Okay. So covalent bonds are when they share pairs of electrons. Two key words here when you think of covalent is sharing pairs. Share pairs.
Sharing is caring.
Yeah, I'm sure you heard that phrase, sharing is caring, after the first time you hit another kid because you wanted their toy, okay? They told you, no, be nice, you have to share, sharing is caring. So in this case, with covalent bonds, they're going to be sharing. So we're going to look at a couple examples of compounds that have covalent bonds in them. The first one we're going to look at is good old H2O. There was a reason we're starting with H2O. H2O, water, is the basis for life. In fact, when we look on other planets or in other solar systems for life, what the first thing we look for is water. So we're looking for water. Water is important for life. You are made, 75% of you, out of water. And you need to drink it every single day. So, let's talk about water.
Cannibalism?
I'm going to use two different colors. I'm using blue and I'm using red. Okay? Blue and red. For my two different elements. I'm going to use blue for hydrogen. And I'm going to use red for oxygen. Guys, let's use what we did up above. What does hydrogen need to be happy? 1 electron. So once plus 1 electron. Oxygen, on the other hand, needs what to be happy? 2 electrons. Yeah. Okay. Now, you guys, we talked about compound formulas first so that you could tell me this. How many atoms of oxygen am I going to draw? Micah?
Oxygen.
Oxygen. 1. How many atoms of hydrogen am I going to draw? Page? 2. Very good. Okay. So I'm going to start by drawing my oxygen first. And the way I'm going to draw it, remember, all I care about are the electrons. So I'm going to draw the Bohr model. So here we go. You can use your Bohr model. You already drew it up above. So I'm going to draw my Bohr model of my oxygen. So it's got, remember, 8 electrons. So there's the first 2. Then 1, 2, 3, 4, 5, 6 on the outer shell. Remember, my oxygen's not happy. It wants to get 2 electrons. So it's got to figure out how to do that. And it's going to do that by bonding with 2 hydrogens. We're now going to draw the Bohr models for hydrogen. Remember, the hydrogen's a nice simple Bohr model. Just got one out of electrons. Now, when you're sharing something with somebody else, you have to be close to them in order to share it. So if you were sharing toys or you're sharing blocks with somebody, you have to sit right next to them. Same thing with these atoms. When they're sharing their electrons together, they're going to be right up against each other. So we're going to draw our hydrogen right here. There's one. Draw my other hydrogen right over here. There's two.
But wouldn't you have to draw on the other electron?
It also has its own electron, which is going to be close to the oxygen because remember, it's sharing it, so it has to be close to the other atom. I'm going to redraw my red ones in here so you can see them. Okay. Now, let's take a look once again at our Lewis structures now that they've bonded. So let's look at our oxygen. Here's our Lewis structure for oxygen. Let's recount how many valence electrons does oxygen now have since it's bonded. Let's look. 1, 2, 3, 4, 5, 6, 7, 8.
What is happening?
Now it has 8. So 1, 2, 3, 4, 5, 6, 7, 8. Oxygen is now happy.
Did it.
Yay, oxygen. So now let's look at hydrogen. Hydrogen. Okay, how many valence electrons does hydrogen have? Lily?
It's gonna have 2.
It's going to have 2. And remember, hydrogen's our exception to the rule. Now its outer shell is full, and hydrogen is happy. All right. In order to make the oxygen and the hydrogen happy, how many bonds did we have to make? 2. Very good. Here's one bond. Notice they're sharing a pair of electrons. Here's another bond. They're sharing a pair of electrons. So we've created 2 covalent bonds here in our water molecule. They're happy. Lily.
I was just looking at this. What would happen if magnesium and oxygen bonded? What would you get then?
Well, you can take a look at that then, okay? It happens.
Oh.
Okay. All right. So the next one we're going to look at is carbon dioxide, another very important molecule. It's what you breathe out every single day. It's what plants take in so they can do photosynthesis. I'm going to use red still for the oxygen, but I'm going to use green for my carbon now because it's needed for plants. So here we go. Carbon. Oh dear. Down for the count on that one. Thank you. And oxygen. Whoa, that's not as good as the other one. All right, what does carbon need to be happy?
4 electrons.
4 electrons. Good job. Okay, what's oxygen need to be happy? 2 electrons. Let's look at our chemical formula. How many carbons are we going to have to draw? 1. How many oxygens are we going to have to draw? 2. So I'm going to start with my carbon. And I need to draw the Bohr diagram from up above. So here we go. The only thing I'd like you to do with this one is make sure that your 4 on your outer shell are kind of paired and apart from each other. So watch this. So 1, 2, 1, 2.
Did you say that electrons are pretty far apart when they're spinning around?
Not when bonds happen. Bonds pull them into certain positions. Because remember, if they're going to share, they have to be close. Right, Lillian? Okay. All right. Now we're going to put our oxygens in. And this is a little trickier. I'm going to be honest, I have a hard time getting this right too. But the outer shell of that oxygen has to come through and touch both of these electrons. Because remember, the oxygen wants 2 electrons. So it has to come in and touch both of those electrons. So I like to do my outer shell first so that I can kind of get that right. And then my inner shell.
Do you have any blood now?
I do, not with me though. Oh yeah, actually, right there. Ooh, come on up and get it. Okay. Now remember, on the outer shell, oxygen has 6 electrons, right? And the carbon needs 4, so it's going to take 2 from each oxygen. So we're going to go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. They are Christmas colors. Let me go back in with my green again so you can still see my electrons from my carbon. Okay. Now let's talk about the carbon. Let's look how many valence electrons carbon now has. It has 1, 2, 3, 4, 5, 6, 7, 8. Okay. And now our carbon is happy. Now let's look at our oxygens. How are our oxygens doing? 1, 2, 3, 4, 5, 6, 7, 8. And oxygen is happy. Now here's my next challenge question. How many bonds did we do? Last question today. How many bonds did we make? More than that. Look at our pairs, guys. Can you hold on one sec? Look at our pairs. 1 pair, 2 pairs, 3 pairs, 4 pairs. 4 bonds.